Yeah, okay. Thank you for the introduction, Thomas. As you mentioned, VTT has been the coordinator of this project. The actually main coordinator is Mikko Pihlahtie, which will later participate in the roundtable session, the panel session. But I have been also working in the coordination team of DriveMode. The DriveMode focus is on integrated modular distributed drivetrain for electric and hybrid vehicles. And here you can see the project overview that, of course, it was the Horizon 2020 EU funded project, and we had 12 partners from 6 different countries. And in this map on the left side, you can see the countries where the partners are from. And also at the bottom of the slides are the logos of the partners. So the project started in 2017 in November. And then it ended actually last month, just 2 weeks ago, by end of March 2021. So in this slide, you can see the objectives of the DriveMode project. If you have previously participated in our presentation, this specific slide might be very familiar to you, but I still decided to reuse this slide since it is just a simple slide, but still include a general overview of the main objectives of the DriveMode project. So the main objective has been to develop efficient and cost-effective drivetrain module for distributed drivetrain. And in this figure on the left, you can see the concept. So what we have developed is a silicon carbide inverter, a highest speed motor, and a highest speed gearbox. And these components are tightly integrated together, and they have formed this one unit as what we call integrated drivetrain module, or IDM. So this concept of being integrated drivetrain module gives us this opportunity to configure the vehicle with 4 power options and also 2 or 4 like wheel drive, as you see in this figure here. And the design is basically suitable for a mass production of all type of the vehicles, basically from very low light duty vehicles to very high performance and heavy duty vehicles. And then here a slide on the motivation that why we have gone for this integrated module and distributed drivetrain. So basically the integrated module simplifies the installation of the drivetrain for the OEMs, as it facilitates the packaging of the drivetrain. And also it would reduce the material usage while it will give the opportunity to optimize the synergies between the components. And then the distributed drivetrain can be used basically, one single design can be used for a large variety of vehicles, which itself would increase the efficiency of the production line. And also it would provide more flexibility in the layout and prepare a better control and more functionality of the system. So in the case that, for example, if a specific torque is required depending on the operation of the vehicle, that torque can be specifically applied to one wheel. And here you can see the target values of the project. So these include the increase in the speed of the motor, increase in the specific power and torque of the motor as well, and also reducing the material that are used for the concept, while also reducing the losses of the system. Each of these targets have been achieved in the DriveMode project by applying or usage of different technical methods And for example, the highest speed motor have a very high power density by using different like advanced optimized solution. And also we have been using a high voltage 800 volt battery system in our design, which itself has given us very good like advantage of being able to control the motor at higher speed very well and efficiency. The usage of this high voltage battery also have reduced the required copper weight of the system, which is also has helped in this material reduction. And for the power electronic component for the inverter, we have used silicon carbide technology, which by itself reduces the switching losses significantly and also allows to downsize the thermal management equipment of the inverter in comparison with the like traditional silicon devices. Okay, so here you can see the task distribution of DriveMode project and also the components that or the prototypes that have been generated in the project. So as you see here, the name of the partners are written next to each of the components that they have been supporting and contributing to each component. So we have inverter, the motor, and the gearbox. For each of these components, we produced 3 units, and then these units, the design part of them were basically done in a loop, as of course their specification was interdependent. And when these units were designed and manufactured, they were like tested individually to ensure that the design values or the targets that were defined have reached. And then, of course, we also have this cooling circuit, which we designed one single cooling circuit for the whole system. And these components were all assembled together as a whole integrated unit. You can see the cat picture of it here. And then when these components were assembled, we had 3 IDM units that were again designed they were tested again individually to ensure the functionality of them. After that, when these units were completed, 2 of them were installed in the vehicle, as you see this scheme of it. So they were assembled into vehicle. 2 of the units were assembled to the front part of the vehicle, and then the 3rd unit we used for further analysis of the drivetrain. So next, I would like to show you some of the design specification of the components. The first one is the inverter. Here you can see that the switching frequency of the inverter is 20 kilohertz. The DC voltage is 800 volt, but it was tested that it can go up to 1000 volt as well. And then, as I mentioned previously, we have used the silicon carbide chip technology in the inverter, and the continuous AC current is 140. And then we have the power here efficiency. The power efficiency is 97% as at the maximum output, and then the power density is about 45 kilowatt per liter. And here the picture, you can basically see the comparison of the inverter itself into a normal size pen here at the figure on the right side. Next, here you can see the motor specification. The picture here is the motor being under the test after it was manufactured. And here on the table, you can see the specification of the motor. It is a permanent magnet synchronous machine. The nominal power is 35 kilowatt. The nominal speed is 8,000 round per minute. Maximum speed is 20,000 round per minute. And then the voltage supply is 750 volt DC. And then this figure is also from the measurement of this setup that is shown here. The blue color ones are what has been like the data that are gathered from the measurement for the drive mode motor. So here you can see the gearbox in the figure, and again it's the setup when it was under measurement. The gearbox has the reduction stage of 3-stage parallel axis, and the maximum input torque is 100 Newton meter, and the gear ratio is 14.1 to 1. And last but not least, this is like the overview of the cooling circuit. So here you can see that the cooling circuit has 4 loops, including this refrigerate loop, HVAC, and then proportional, and then the storage system coolant loop. As you can see in the figure, all of these loops, like the circuits, they are connected with each other. We have one extra loop here, which is related to the onboard charger loop. And only this one is like separated from the whole system. And so this coolant circuit was designed so that it can allow maximum of 65 degrees Celsius of heat of temperature, and also minimum flow rate of 10 liters per minute. And here you can see again the design, the 3D CAD view of the components which are integrated together with their like specific specification for each of the component next to them. And here on the right side, you can see the pictures of the units after they were manufactured and ready to be installed on the vehicle. So here in the figure, you can basically see the important feature of the drive mode IDM, that it is integrated, and it gives the possibility to have this distributed feature on each wheel of the vehicle. So when these IDMs, as I mentioned, were ready, we provided or we planned testing for them. This testing, the aim of the testing was to validate the system performance and also to validate the efficiency of the IDM and the motor as well. So here you can see the tests that were planned for the IDMs. So basically the acceleration and also driving the IDM with different like a speed at different gradient, and running it at the peak torque or power, and also calculate or measuring the efficiency data. Here on the right side, you can see the outline of or the layout of the testing system that was used for the drive mode, the IDM testing. The black blocks are the components of the drive mode, and then these blue ones are the load side of the testing setup. The load was the load here, you can see that it is controlled by a speed, and then the drive mode IDM was controlled with the torque. To make the testing easier and to facilitate the testing, as since these testing were quite intensive and long, we decided to provide this sort of canalizer panel, which helped us to somehow automate the testing. So this means that we could define each of these tests as an input file and give it to the computer, and this canalizer panel would automatically run the tests according to the input file that was provided to it. So next, I would like to show you some of the results that we gathered. Okay, no, before that, here I have one video. Since it might be slow, I will turn off my camera. Hopefully you still can see my screen. So this is the video that was captured during one of the testing of the IDM. You can see here is the load side, and then the drive mode, the drivetrain is like the drive mode IDM is behind these fans. And here you can see another picture of the setup from the other side. So you can see behind this block here. And this testing was, this video was taken during the testing at Danfoss facility in Lappeenranta, Finland. Okay, and then after that, here are some result efficiency result of the IDM. So basically, these are like for different speed round per minute and different torque Newton meter for different operating point. And here are the efficiency of the machine alone, like the motor alone. And as you can see, we have reached the maximum efficiency of 97.3 at this operating point of about 8,500 and round per minute, and the torque of 27.6 Newton meter. Just to have a better comparison between this measurement result with what was designed initially, here I have put the data on the efficiency map, which was calculated in the beginning, in the design phase of the project. And I have put some of these values on the map to see that not only these values matches what we have designed for the system, but also we have reached this expected impact of the project that was 50% less losses for the motor, which the aim was to increase the efficiency to more than 96%. And here you can see that there is the maximum efficiency is 97.3%. So next, again, I want to show you this expected impact. That's how about the other expected impact of the drive mode project or the call. That was a 30% increase in a specific power and also an incremental reduction in the total cost of the motor. So for this, we have done some comparison between the drive mode motor and like the other traditional traction drives that are available. And for the case of this total cost reduction, we have compared the amount of raw material saved per kilowatt of the mechanical output power of the motor. So in this slide, my next slide. Okay, in this slide, you can see this comparison. So this is the drive mode motor versus other automotive, that was BMW i3 and Volvo XC90. Here you can see for this third row is the measurement value for the drive mode as at 6,700 round per minute, 110 Newton meter. And here we have the specific power, kilowatt over kilogram. And for the total total material, and here we have only specifically for the permanent magnet. As you see, this value is quite similar to the BMW, but more than double for this Volvo. Of course, in the case of BMW and Volvo, these both of the values are in the case of overload, whereas here in the drive mode system, this was not overload, but it was measurement. If we compare the overload, we see that even the difference of the drive mode is much higher than the other two motors. And then again, the same thing is applicable for the specific power of permanent magnet, if we only consider the permanent magnet. And in the next slide, I have done a comparison between the drive mode motor versus this DOE's Department of Energy of USA. So these are like the target of DOE 2022 targets. And here you can see for this target, the specific power is 1.6, whereas for the drive mode, specific power is 3.4. And then we have the expected, another expected impact, 30% increase in the motor specific torque. This specific impact was not achieved in drive mode, and the reason for is that the drive mode motor was optimized for the power, but not for the torque. So the drive mode motor was designed for the peak power of 100 Newton meter, but we have achieved during the testing to up to 110 Newton meter. And this was definitely achieved, but this 30% increase was not achieved. Here you can see the comparison of the drive mode, the measurements and the calculated value versus again, the BMW overload. As you see, the values are lower than the torque which BMW has. But again, if we compare the total torque of the system, like the whole drivetrain, you see that drive mode still achieves higher values for the specific torque in that case. Okay, we have done also some comparison between the for the inverter or the converter. Here you can see the comparison of the drive mode converter with one of the IGTB converters that our partner who developed the converter they provided. So this is one of their converter that they use, and then they have done this comparison of the price. So as you see, the control drive board, both of them have quite same price level, but then the housing is what makes the biggest difference. And in overall, we see that the drive mode converter has about more than 10% of increase in the decrease in the cost. And then here you can see the power density that increasing the power density by 50% is fulfilled. Again, this comparison is with the inverter of Semicron, one of their converters that they like commonly use. And here also some comparison of the losses that we can see the numbers here, but now I see that my time is like quite running short, so I will go a bit faster on this slide since they will be also covered during the panel session as well. And we have done also some comparison between the drive mode inverter with other current state of art, let's say, because this is like from 2020, and then this is the latest production of Bosch, that we see that the power density of drive mode is more than double of this, and also the efficiency still is in the same range as this Bosch power electronics. And then a bit about the assembling of the vehicle. Here you can see the outline of how the vehicle was designed. In the front, we have two IDMs. At the back, we have the onboard charging setup. And then in the middle, it's the 800 volt DC battery pack. And then here you can see the mechanical integration of the front part. Here you can see the drive mode IDMs installed in the front part of the vehicle. And then also here the figures some figures from the vehicle after it was completely assembled and ready for testing. So this is taken from Neves, Sweden, because they were responsible for the vehicle testing. And you can see that we have put also this logo of DriveMode and the logo of the partners, and of course the logo of EU and the project. So some comparison between the driving cycle analysis of the vehicle. So here at first we have put like this table includes the NEDC and WLTC driving cycles and the consumption of the vehicle in this column, and a quick comparison with other car manufacturer. We see that basically the value that we have got puts the DriveMode vehicle somewhere between BMW and the Porsche, which is quite good achievement of the project, although it was not the main focus of the project. And then after that, we have this some values for the vehicle performance. At first, we have this acceleration test where the vehicle speed was increased from 0 to 50, 0 to 100, and 80 to 120 kph. And here you can see that two different tests were done, one with 110 Newton meter, one with 95 Newton meter. And here are the seconds that how long it would take for the vehicle that, for example, reaches from 0 to 100 to which was 9.81 seconds. And then again here for the top speed, driving the vehicle at top speed at 0 gradient, 4% gradient, and 12% gradient. And we have done this comparison with the design target value, which was defined in the beginning of the project. And you see that for the 0% gradient, the drive mode vehicle is the top speed is lower than the design target. The main reason for this can be that the drive mode had more components inside the vehicle as compared to this design. Sorry, this was so the design is like the speed is lower than there, but then for the 4% and 12%, we see that we have achieved higher top speed in this case. One point here I wanted to mention is that this design value have been designed for the gear ratio of 12.1, but later on as we moved in the project forwards, we changed this gear ratio of the gearbox to 14.1 to 1 rather than to 12.1. And at the next slide, I would like to show you my next video of the I stopped my video now, but I want to show you this demo vehicle video because we were supposed to show this in the actual event to the audience, but unfortunately it did not happen. But we have this video of the vehicle running at the test track of Neves in Sweden. And since there might be a problem with the video playing here, I have put the QR code for the video from YouTube, from the DriveMode YouTube channel, where you can basically scan it and watch it with a better quality perhaps. So as a conclusion, I just wanted to show this expected impact where later on it will be discussed more in details that drive mode has achieved almost all of the expected impact except this 30% increase in the torque, and the reason for that was the motor was optimized for the power but not for the torque. Other than that, we see that all of these expected impact have been satisfied. And thank you very much for your questions. So now I'm open for questions. And of course, here is my email address if you would be interested in the project and would like to keep contact regarding that. Thank you.
Thanks a lot, Mernat. Very nice overview on the journey of your project and summarizing the final results and also the limitations, of course. So one thing is design, and one thing is reality. We will see this in the other presentation as well. There's a lot of questions. I try to condense, cluster them a little bit for you. There were a couple of questions regarding the permanent magnets in the motor. Is it, I guess these are traditional rare earth neodymium dysprosium magnets, and are they inserted in a special way into the rotor?
Yeah, they are. And then the design of them have been very unique, because we have got the design of as I mentioned during my presentation, the design of like the location of the permanent magnets are defined by the optimization like procedures. But yeah, they are like interiorly in the rotor of the machine.
Okay, there was a question, but I think in your presentations, to me, it was pretty clear. 97 point something is the peak efficiency of the electrical machine.
Yes, that is what
2.6 liter, was this the volume of the machine or active parts only?
let's see. I have not included the volume of the machine in these slides. It was the inverter that I included.
Okay, maybe Miko can check this and answer here in written to this question. What was the benchmark of your motor? Was it the BMW i3?
You mean for the vehicle?
Yeah, for the IDM and specifically for the e-machine.
Yeah, I think that one my colleague can answer if he's available for that. Damian, are you? Because they
Yes, so Damian is now in the list of panelists.
Yeah.
So Damian, you can take the floor. You can unmute your microphone and take the floor. Yeah.
Well, everybody, I'm Damian Milevec from University of Ljubljana. And if I may answer this question, yes, the benchmark was done, let's say, more in focus to the BWM i3. And it was done because we think that that kind of motor, or the motor of this vehicle, it's, let's say, state of the art nowadays. So we try to achieve, let's say, the same or even better characteristic that as that machine. So Mernas, if you can go to the comparison between this our design and the BWM. Back one, please. Yeah, thanks. So firstly, I have to point out that it's very difficult to get such information. We, let's say, took around the internet and found some benchmarking done by Americans, and we found this data on their site. This is firstly, we didn't bought and let's say cut the machine and see what is. It was already done by I think it's Oak Institute. So, and then we say, okay, we would like to be better than, so that better than this BWM. And so we try to reduce the amount of magnets. As you can see here, we achieve quite high number of kilowatts per kilo of magnet, as we see here. Now, the measured data as are presented are due to, let's say, not that there are limitations, but within the project, we defined that the inverter power or the inverter current limitation will be set to 140 amperes. So according to that, it was one kind of our boundary condition for the design. And the other boundary condition was also 20,000 RPM of rotational speed. This is also, let's say, we bring above state of the art regarding the rotational speed, where the mechanical stiffness is still compact. So motor can run, and it runs at 20,000 RPM without mechanical damage. It was tested up to 25 and calculated the safety, let's say, rotational speed up to 30,000 RPM, but we are using just up to 20,000 RPM in accordance to the gearbox ratio. And this gearbox ratio was 14.1 to 1. That means with all IDM, we can achieve 180 kilometers per hour. So our machine goes 20,000 RPM, including the gear ratio, and we have at the end a final speed of 180 kilometers per hour tested. That is firstly. Secondly, we achieve lower permanent magnet consumption. That means we are, let's say, going towards the green solution. Also the structure is, the rotor structure is patented because of this high speed rotation. Okay, I thought that I answered the questions, so I'm going.
Yeah, sorry, Damian. Yeah, very interesting details, and I think people can definitely follow up with you directly. Maybe a quick question, if you can answer it quickly or give a reference where people can find this. There were two questions regarding system cost efficiency, and one specifically, how does your integrated system compare to traditional non-integrated systems? So is integration adding complexity and adding costs, or is it cost savings?
Let's say, if I may answer, we can say that it is cost saving because everything is, let's say, smaller. That means that less material is used, just or raw material is used to produce such IDM. Then everything is compact. It means that it's changeable, so that means it's modular. So we can use this drivetrain as a single IDM, double IDM, so each wheel, or even four-wheel drive. But we have to go further on with the development. That means that we have to implement or also torque vectoring for the better performance, as it is in, let's say, new Audi e-tron. So we have a lot of challenges after a good result, so we can go further on to improve the let's say, the whole drivetrain possibilities.
Okay, thank you. Yeah, I think we could discuss for hours. There's still some questions left in the Q&A. Maybe you can meanwhile answer some by written.